Hello everyone, welcome to the fourth in a series of webinars hosted by the Stockholm Environment Institute. It's webinars to discuss the Gates Foundation sanitation grants. I'm Arno Rosemarin, and along with me Nelson Ekane from SEI. He'll be running through the different presentations. The whole thing should take 45 to 50 minutes, we hope. Before we go into the three speakers, the three groups of research people, we would just like to introduce you to some of the participants for today. And we have a number of interesting people. If you see to the left of the screen, there are registered people from the US, from the UK, from Ecuador in South America, from the Netherlands. And it's a rich array of people that have received grant money from the Gates Foundation. In addition, there's a couple of SuSanA members of the Sustainable Sanitation Alliance from the US. And on top of that, we've got the SEI project team that's been working with the Gates Foundation to get these grants onto the SuSanA system. As I scroll down here, you can see those two people are Dorothy Spuler from Ekane in Switzerland and Elizabeth von Munch from Ostella in Germany. From the Gates Foundation itself, we have Deepika Ailani and Roshan Shrestha, and they're both here hooked in from Seattle today. A little bit information about the where this is going. This will be a recorded webinar. It will be on the SuSanA discussion forum, and you can see that red link down there. You will be able to find out more about these speakers as well as the other grants that we are looking at in this program. Just a bit of further information, there will be two more webinars planned, one on the 15th of January and one on the 4th of February. So before we waste any more time, I'd like to give the word to Nelson Ekane, who will be chairing the three papers, and he will be introducing the speakers.
Thank you very much, Arno. We're happy to have three experts with us here today, basically from the US and the UK. We have Alison Parker from Cranfield University. We have Jeroen Ensink from London School of Hygiene and Tropical Medicine in the UK. We have Richard Fisher and Ryan Mahoney, University of Colorado, USA. So you all have 5 minutes each to present. You can continue for a couple of more minutes if you need to allow. We need to have some time for discussion because we have so many participants joining us today. So without wasting time, we'll ask Alison to start. Alison will talk about nano-membrane toilets. Alison, please.
Hi everyone, thanks for the introduction, and it's really great to be here and speaking to so many people all over the world. So I'm going to tell you about the nano-membrane toilet, which we've been developing under the Reinvent the Toilet scheme. As you can see from the photo on the lead slide, or it's not a photo, it's an image, the nano-membrane toilet is a household scale toilet, so it should fit into bathrooms or toilet structures or superstructures. So our design team have worked hard to ensure that it's an attractive, desirable and an aspirational product. Next slide please. We found it was absolutely critical that there was a flush mechanism that worked, that was desirable for users, going to separate them from their waste, both visually and by smell. So the illustrated here has when you lift the lid, there's a bowl that's presented. This can take both feces and urine. As the lid closes, the bowl rotates, and then it's scraped clean. And in this way we can flush that no water at all does it achieve that visual and smell separation. Next slide, please. So after the waste is flushed away, it enters this chamber, and in the chamber are some membranes. The membranes are hollow fiber membranes, so they're kind of long tubes of membrane, and a dry sweep gas passes along the inside of each tube, each fiber, and water is run through the membrane walls as a vapor. Because the membrane's non-porous, very small molecules pass through, and actually water is the smallest molecule in human waste, far too large to pass through our membrane. The membrane is hydrophobic, so it isn't wetted and hence foul. So we've now removed the water. Next slide, please. Next slide. The water is condensed on two bead columns. We're experimenting with different materials for the beads and different coatings for the beads. So what you see here are glass, the blue-coloured ones, and the red-coloured ones are silica. The water is condensed onto these beads and then can drain out. And that water is also clean enough because there's no pollutants in it that it can be used around the house, washing or irrigation. Actually, it's clean enough that it could be drunk, but there may be some taboos around that, so that's not. So that leaves us with the solid waste. So next slide, please. So back one, the Nano Mister slide, please. Thank you. This is the Nano Mister. So this creates a mist of water, and suspended in that water is polymer. So this polymer creates a coating over the solid waste, which stops smell and pathogen escaping. So next slide, please. This is all the components together in our what we're calling our works-like prototype. So this prototype illustrates how the components will be configured together. As you can see, it's made of perspex. This is the final design. It's not made of perspex because we appreciate that not everyone shares our fascination for looking at how our waste is processed. So it will be an opaque and quite attractive design, but this shows the components together. So you can see in the front center, you can see the chamber with the membranes in, and the flush will sit on top of that. That's the one component. As you can see at the moment, we're near the end of the cycle, so most of the liquid has been extracted, and you can see the liquid in the container at the bottom. The solid is just settling at the bottom of the chamber now, and is being moved out of that chamber using a screw press, and this extracts the last of the liquid from the waste. And then you can only just see on the right-hand side, middle right-hand side is the Nano Mister. This is where the coating is applied, and you can see some of the waste sat at the bottom right. The bead columns on the left. So that's the works-like prototype. The power for the toilet will be supplied using by using human power. So we've been developing various bicycle and hand cranks. There's only a minimal amount of power needed for the toilet, simply for the sweep gas for the membranes, Nano Mister, and for the screw press. So it can be supplied by mains quite easily, but obviously we're looking at scenarios where the mains electricity might not be available, so this bicycle generator could provide the energy for the toilet, and any excess energy that's generated could be used for charging mobile phones or running a TV or any other use around the home. Next slide, please. The phase that is still is really the biggest area that we still need to work on is extracting energy from the solid. So there are various other grantees who are working on options. We would plan that the solid waste would be taken from our toilet once a week, away to be processed and for the energy extraction. So we're looking working potentially with Janiki, who are developing one option for composting. We're looking at Unilever, who the photo on the bottom right, they're working with a company called CCS Limited, who have a pyrolysis unit, which you can see photographed. We've also seen some examples of very small-scale gasifiers, which would work on maybe just 40 households' waste to extract that energy. So the type of business model we're proposing is that users would pay a fee to have this waste extracted once taken away from their houses once a week. They would pay a fee for this service. The service would also have a monthly maintenance cycle, which will be required, and also will be a partially rental fee for the toilet. So under contract, they won't pay a large upfront cost, but will pay a small amount every week. Next slide, please. So obviously, this is not something I'm working on alone. We have a large team here at Cranfield working on the design, the engineering, the nanotechnology, the waste treatment aspects of the project. And you're very welcome to go and look at our website, which is listed there. We have a blog as well with plenty of photos and videos of, especially at the moment as we're really at a very much at a building phase. There's lots of new equipment coming in, and you can see videos of that working. We're welcome now, but if you've got any the areas of collaboration.
Thank you very much, Alison, for that brilliant presentation of a very high-tech system, at the same time very practical, the use of the bicycle, manually powered system. We are quite many today, and I would like to give the floor to the audience for questions, for a round of questions. I see two people raise their hands. Luisa Campos, you have a question to Alison?
Yes, Alison. Unfortunately, your message was cut here as well. Although we are in the same country, I couldn't hear very well. But anyway, very interesting, and very interesting toilets were developing there. I couldn't get much about the nanoparticles of the water, the small molecules that form it. If you could explain a little bit more about that. I couldn't understand if the water is being treated and then you're going to reuse it. And also how that compares with the urine diverting toilet. And in terms of costs, I would ask you.
Alison, questions for you?
Yeah, Louisa, do you mean the nano coating for the solid waste, or the membrane that is separating the waste, the water from the rest of the waste?
Yeah, you said that some water molecules, they go to that beads column. Mm-hmm. I don't know if that's purifying the water, and then you're going to reuse the water. And my other question would be in terms of costs. How much your toilet would cost in relation to the simple urine diversion?
Okay, Louisa, to answer your first question, the water that passes through the membrane is essentially pure water. The only thing we think might pass through it might be some of the volatile organics. So the beads, because the water is a vapor, the role of the beads is to condense the water. Rather than to do any purification. If there's ammonia, for example, that's passed through as a volatile organic, that will be absorbed at that point. But there will certainly be no pathogens. Does that answer that first part of your question?
Louisa, are you satisfied with that answer?
So just use the positive. Yes, that answered the first.
Okay, great. There was also a question of the cost.
On the costs, so like all the other grantees, we're aiming for less than 5 cents per user per day. And we do think this is possible, although it does look like a very a high-tech system. It is using components that are essentially off-the-shelf. The membranes are off-the-shelf components. They're not something that we've developed especially for this toilet. So we think we can get the overall cost to manufacture the toilet down pretty low. And with the energy generation, we should be able to offset some of those costs as well. So yeah, we haven't got the financial modelling done completely, because we're still really only just pinning down exactly how the technologies will work. But we think that we're confident that we can get below that 5 cents per day, which was the target that gave.
Yep. More questions from the participants. You can actually click on. You put your hand up by clicking on the icon at both. Yeah, we have Dorothée. Dorothée, please. Go ahead.
Yeah, listen. My question was regarding the reuse or the treatment of the different products you have. So you have the solid parts and the liquid parts, right?
Yeah.
Did you already test this toilet with real products, real users during a period?
So we're at the level where we're testing with synthetic feces. We kind of really want to get on with testing with real feces, but we're aware that it'll kind of potentially make the system a bit unclean, and if we need to export it anywhere, then that's going to be a problem. So we're testing it with synthetic feces at present, but we really want to get testing with the real stuff.
All right. Any more questions? Yes, Mark, please.
Yes. Hi. Thanks for taking my question. Alison, I was wondering if you're concerned about decrease in permeability of the membrane over time, maybe by plugging salts or by
so in terms of fouling,
growing
because
biofilm
the membrane
inside
is
the membrane?
hydrophobic, it doesn't get wetted, so the usual kind of fouling problems that are associated with membranes won't happen because it isn't wetted and the water is actually passing through the vapor.
But so you have long-term tests that show that
I
water
wouldn't say
flushes are constant over
long-term,
time?
but that's certainly what we're finding so far. And it, like I said, it is an off-the-shelf membrane. It's not one that we've developed, and there's been no problems reported. But yeah, certainly we're looking forward to moving into a longer field testing period. Yeah, we'll get an answer to that. But the theory doesn't suggest it'll be a problem.
Thank you.
All right, thank you, Alison. Just to, if there are no further questions, then we can move on. But before that, I have just a question on you said they're free. Did you do some tests and the microbial tests? And if you did, could you share those values with us? And also the nutrient content of the sludge. Did you do any tests of the NPK, for example?
Sorry, what was the first question? What you said was free?
Yeah, you said it was pathogen free. Did you do?
Because we haven't tested on real feces yet, no. But because the pathogens won't be able to fit through the membrane, because there's no holes in the membrane. Essentially, the dense membrane. We don't expect any pathogens through, but obviously we need to back that up with tests once we're working with real feces. And your second question, I've forgotten. Your last part of your question?
Yeah, the other part of the question was on the nutrient contents of the sludge, the NPK. Did you do any tests on that yet?
No, because we're anticipating that we're basically going to thermally process the sludge, so we are going to lose those nutrients. But we think that that's a more cost-effective mechanism than potential fertilizer reuse. Energy is extremely valuable, whereas reusing fertilizer in urban areas has proved challenging. So of course I'm keen to hear examples of where it's working well, but we think that the thermal processing energy is going to be the.
All right, thank you very much, Alison. So we move on to Jeroen Ensink. Jeroen is from the London School of Hygiene and Tropical Medicine in the UK as well. and he will be telling us about new concepts for on-site sanitation based on bio-additives and pit designs. Jeroen?
Good afternoon and good morning to some of you. I've had a long discussion with Elizabeth on what I should present, because we are a 5-year grant if we take the no cost extension in consideration, and we've looked at consumer demands, we've looked at different designs, we've taken products to market. But I thought to focus on kind of the fundamental pit latrine research that we did, which was one of the things requested to us by the Gates Foundation. And it kind of started off with kind of this story that we probably have all heard. Some pit latrines fill up within 2-3 years. Other pit latrines seem to last forever. So our question was, what is there in the pit latrine that makes a latrine perform well? And if we know that, can we change design, or could we possibly work with bio-additives to speed up the process? And as you can see, it's not just me. Stephen, who's participating today, was part of the project too. And I think I would just like to start off with the next slide. So our objectives were to identify kind of components that could accelerate decomposition in the pit latrine, but also look at the influence of design, management, environmental conditions on decomposition rates and pit lifetime. And what we did for this, that we selected 50 latrines in Tanzania and 50 latrines in Vietnam. We followed them over an almost 2-year period. We did stool surveys, we collected fresh samples, we analyzed them for a variety of biochemistry and physical characteristics. We weighed them, but the most important thing that we did was, over a period of that 2 years, we monitored latrine fill-up. Could I have the next slide? And the way how we measured latrine fill-up was with a laser reader. Every 2 months we went to the same latrines, took a fixed point, looked at the volume change in the pits. At the same time we did questionnaires, observations regarding use and management of the latrine. And the slide, well, the image next to the photo kind of shows the variety in pit latrine fill-up that we found. So we had some latrines that over a 2-year period seemed to accumulate less than ½ liter per person per day using it, but we also had latrines that seemed to accumulate almost 2.5 liters per person per day. So we have a wide variety in different latrines with different fill-up characteristics. Well, next slide please. When we looked at those 50 latrines in Tanzania and Vietnam, we could classify them based on their fill-up rate, so the FUR. If the fill-up rate was less than 0.1 liter per person, we considered this a good performing latrine. The yellow ones with a fill-up rate in between 0.1 and 0.5, normal performing latrines. And then we had the poor performing latrines that have more than 0.5 liters per person per day. So this is how we classified latrines. At the end of those 2-year periods, we took a core sample through every pit latrine, and that material that we collected was analyzed for a variety of different physical characteristics. It went to the SuSanA Institute to do a full blast of all microbiota available in that pit latrine, whether alive or dead. We did detailed digestion analysis at Wageningen University, and we looked at the bottom of the latrine what kind of material was still there, and that was done by NMR analysis, solid state analysis, which should allow you to give a bit of an idea about what is still there. Can I get the next slide? And I think I'm just very quickly going to run you through some of the findings, and I'm aware that this is not the most clear slide. I think the story with it is actually more interesting, is that when we looked at the latrines, we came to the conclusion that roughly 60% of all COD available in a pit latrine does not react at all. So it's basically inert, it stays in the pit, it doesn't react. That's the first conclusion. Next slide, please. Could Could I get the next slide? Oh, sorry. Yeah, this one. The other observation that we made from the biodegradation work was that if we look at the 50 latrines that we have, we kind of roughly can classify those 50 latrines in 3 groups based on their biodegradation. We have a group of latrines, and these are the kind of the green and brown lines at the top, a group of latrines that at the moment that we put them for biodegradation, they start automatically producing gas, so biogas in this case. Then we have a group of latrines, and those are kind of the middle ones, from the blue to the kind of orangey browny one in the middle, latrines that initially do not produce any biogas. But at the moment that we add an inoculum, and in this case the inoculum is Dutch wastewater because these tests were done by Wageningen University, after the addition of the inoculum, suddenly the sample starts producing biogas, so the sample becomes biologically active. And then the bottom one, the red and the light blue ones at the bottom, we have a group of latrines that, irrespective of an inoculum added, they do not produce any biogas. There is basically no biological activity in the pits. So I thought these were very interesting findings. So a latrine automatically producing gas, some latrines that start producing biogas, indication of biological activity after an inoculum, and some latrines that simply don't do anything. Then, next slide please. This led us to the following assumptions. There is a part of fecal matter which is very difficult to degrade and that stays behind. When we look at kind of the bottom samples in the latrine, so going from 1,50 meters to 2 meters at the top, really at the bottom of the pit latrine, there is a lot of material left over there. The NMR analysis seem to indicate that the material that doesn't get degraded probably is complex polysaccharides and lignin. We need to look into much more detail, but wet chemistry is expensive and really time consuming, and we're still trying to work on that. But if we know what that material is in the bottom of the pit latrine, the material that doesn't degrade, then there is an opportunity to find enzymes or something else that could actually help break down that 60% of material that doesn't seem to degrade. Environmental conditions are unsuitable in the pit latrine to keep key microbial communities alive. What we see in our data from the SuSanA Institute is that we have very different microbiota in pit latrines that perform well as compared to latrines that perform really poorly. We have at the moment kind of identified a group or different families of bacteria that are associated with good performing latrines, but open up the potential that which I was initially a bit skeptical about, but that we could come up with a bioadditive. Then in addition to that, we found latrines that are really low in moisture contents, which could limit biological activity, and we have latrines that are really wet, which could limit biological activity. pH and temperature, etc., are also key issues. And that kind of links us to the bottom of to the last point. It does seem to suggest that there are some microbiota missing from from poorly performing latrines. We are looking at the archaea data at the moment. That's the last bit of data that we're processing. So those are the methane producing bacteria which are associated with, or which would we assume are associated with better performing latrines. But our general assumption is that, well, there are bits and pieces of microbiota missing in bad performing latrines. And I think that's the broad story that I wanted to tell you, and I kind of end with the slide on who we are. We are a much larger grant. We are a mixture of academia, so what I'm presenting today is actually just the fundamental research on pit latrines that we've been doing, but we've been developing business, we have been developing prototypes and have been testing prototypes. And if you want to know more, please go to the website and look at the different work streams that we have. I'm in the process of updating the website, so there should be new information for you soon. And I assume that I'll now stick to the 5 minutes.
Thank you very much, Jeroen, for that presentation. It's interesting to know what is happening in pit latrines, because it's actually a place where so many things are dumped in. So we will go for a round of questions. Yeah. Elizabeth has a question.
Yeah, thanks very much, Jeroen. I have two questions. One is, for me, when I thought about pit latrines that fill up fast and that don't fill up fast, I always thought the main factor would be the characteristics of the soil, whether it's draining the liquid or not draining. You didn't say anything about that, so I'm just wondering, how did you take that factor out of the equation if you felt that that's not what you want to study here? And the second one is about these pit additives. You know, there's so many suppliers out there on our discussion forum. They often try to flog their products. What would you say, what's the thing that if a supplier says, hey, I've got this great pit additive, what is your question back to the supplier to prove very simply whether this is bullshit or whether this is actually something worth?
Okay, thank you very much. I think to the first point, I think we all know that a poor draining latrine will fill up very quickly. We purposely selected in Tanzania latrines that were all free draining. So even within the free draining latrines, we still have latrines that fill up very quickly and latrines that seem to last for 30 years. We have the anecdotal latrines where people say, like, well, I built my latrine 15 years ago. I never had to empty it. I never had to move. As part of our project, to answer your second question, we have looked at different commercially available bio-additives, so kind of also doing a bit the work that the University of KwaZulu-Natal has been doing around pit additives. The pit additives that we found, or that at least that we brought back with us, none of them worked. We also work with Novozymes, which is our large enzyme company from the US, and we have some strains, and in our lab setup, some of those strains seem to produce a 15% more rapid decomposition of material. What I would ask to a consumer, to somebody selling them, I would literally ask, like, well, what is in it? Which in most cases they probably won't tell you what is in it. It's probably going to be a mixture of different bacterial strains. The problem, of course, is that for a bioadditive to be effective, you first need to create a large amount of bacteria, which will initially increase the amount of material in your pits. I'm not sure what I would ask them, but as I said, I think when we started off this project, I was very skeptical about the idea that there could be some sort of bioadditive that could be added to a pit latrine. But we do really see in our data that there is certain microbiota that is in good performing latrines, that is clearly not in poor performing latrines.
All right, thank you, Jeroen. There was a question from Daniel to you. Is asking if you have collected data on demographics, diet, and so on, and try to correlate this to sludge digestibility.
Yes, we have data on diets. We have an incredibly large database at the moment, and we have special help from statisticians, Chris Quint and Uma Ilias at Glasgow University, to help us make sense of it. So we have diet data. We are looking into these kind of things. The problem is that we have a very uniform diet in rural Tanzania. Having sampled latrines for weeks at end, it's going to be rice and beans, more or less all the time, and here and there some maize. So especially the diet in Tanzania is very uniform. The data from Vietnam should give possibly maybe more insight on the impact of diet on digestibility of material.
All right, Dorothy, you had a question too?
In the chat, it was related to Daniel's question. Do you have data also on the frequency and purpose of usage? Because you can have, within a number of 50, you can have quite high insertion.
Sorry, I missed the first bit. What was the first part of your question?
My question is, did you correlate, besides the data on diet, did you correlate also to the data on usage and purpose of usage, because you can have a high insert?
Yes, so as I said, the data is huge. I think we're probably at the moment at something like 50,000 different variables, not even taking all the variety and microbiota data in it. We do all the analysis that is needed to correlate and control for different factors.
Okay, any more questions? Mark? And then Chuck?
Yeah, very interesting study. What I was wondering is if you had attempted correlation with things very simple that are known to affect anaerobic digestion in methanogenesis.
I think the key thing that at the moment that is showing up as a correlation between good performance is, well, in the lab experiments that we have, it's certainly moisture content. There needs to be a certain amount of moisture to make sure that there is activity. And phosphates seem to be more associated with poorer, with better performing nutrients. And then, of course, pH and temperature do play a role, because they effectively at one point stop processes if they are outside certain bands. We did find some latrines that were highly acidic, but we had pHs in Vietnam and some of the latrines of 5.5. And we had latrines that went up to kind of more base, so over 8. But the majority of the latrines actually were somewhere between 6.2 and 7.
All right, Chuck?
Okay.
Chuck, are you still there? You had a question? Yeah, Chuck is not there. So we move on. If there are no questions, Laura.
Can you hear me?
Hello, Laura.
Oh yeah,
Yes?
Sorry, can you hear me?
Go ahead.
Yeah, I was wondering, Jeroen, thanks for your very nice presentation. I was wondering if you had any research on the caloric values of the different pits. It's probably just beyond your scope, but I was just thinking.
No, sorry, that we don't have.
Okay. Or any other kind of chemical consistencies of those pits that might be useful for the other teams? Are they shared, or could we find them anywhere? Or?
We're in the process of publishing our first paper on kind of microbiota and kind of chemical analysis. If all goes well, and I'm sure we shared it on the SuSanA website, we have papers coming out on the different aspects, so performance, chemical characteristics from top to bottom for all latrines. So I think give us a couple of months and then it should be appearing.
Okay, cool.
Yep.
Thanks a lot.
Jeroen, yes, let's move on. I think that's very interesting. It will be also interesting to know exactly how papers, plastics, and pads affect biodegradability. But we may discuss that on the forum further. So we move on to the next presentation. Richard Fisher and Ryan Mahoney from University of Colorado, USA, will be presenting soil char toilets as using concentrated solar energy to stabilize fecal waste and produce a valuable soil amendment. Richard, Ryan, I don't know how you manage this, both of you, but you can go ahead.
All right, hi everybody. I'll go first. Thanks for the nice introduction, Nelson, and for the other presenters. It's been a really interesting webinar so far. But yeah, we're with the Solchar toilet using concentrated solar power and fiber optic cables to transmit our concentrated solar energy to pyrolyze and disinfect waste, at the same time producing a useful biochar product. So go ahead and move to the next slide, please. So we have parabolic mirrors that concentrate solar energy. In terms of concentrating solar, parabolic dishes sort of the parabolic dish as opposed to parabolic trough gives you the maximum, the highest concentration possible and highest optical efficiency. We use fiber optics to transmit that energy to a pyrolysis reactor. Essentially, typically in CSP applications and concentrated solar power, you need your reactor to be at the focal point of whatever light you're concentrating. And using fiber optics essentially allows you to bring the focal point to a reactor somewhere else, and theoretically anywhere, as the fiber optics can fairly effectively transmit solar energy. The reactor is sort of just a cylindrical reactor that sits on a carousel. You can kind of see it in this drawing on the slide. And we have two reactors that in one mode it's acting as a collection vessel underneath the toilet, and then it rotates around the carousel to the other side, and the fiber optics kind of drop down over it and add heat to the reactor and stabilize the waste and produce a useful end product of biochar. So next slide. This is sort of the artist rendering of our prototype that we have. It's actually sitting out in the parking lot here at CU. We're testing, it's a nice sunny day, so we're testing our reactor right now. And so you can see on the right side of the image is the 8 parabolic dish solar concentrators, and the fibers are not shown in this image. I think it makes the SolidWorks simulations a little bit cumbersome. But then, similar to the drawing before, you can see the reactors underneath the toilet, and we have this kind of on a mobile cart that allows us to move the whole prototype out to wherever we'd like. So next slide. So the idea behind using concentrated solar power is, one of our most abundant resources is the light from the sun. And so we can efficiently concentrate that energy up to about 2,000 times. So if you want high temperatures in your reactor, you need high concentration. So theoretically, I think the maximum is around 5,000 suns. So we're not quite there, but it's pretty considerable concentration. And we're expecting to see anywhere from 500 watts up to 1,000 watts of delivered power, depending on weather conditions and the quality of sunlight for the day. We'll actually be able to nail that number down after today. We're testing the fiber optics that we're going to be using in our prototype that will be sent to the fair. So if any of you guys are at the fair, you'll be able to see it in action pretty soon. So I'll turn it over to Ryan. He's going to finish up the presentation.
Yep. Thanks, Chip. Hopefully everyone can hear me. This is just a quick overview of we are using urine diversion, and we have the urine circulating around our reactor to take advantage of some of the waste heat around the hot reactor. The urine is just targeting 70 degrees C for 30 minutes in order to disinfect it. And we have a dumping mechanism on our current prototype, and so it'll be easy for people to use. You can go to the next slide, please. So overall, we have a first generation prototype that we're finalizing the construction of right now. We're mainly trying to prove the concept and make char out of human waste using concentrated solar power. And so it's designed to meet the needs of 2 kilograms of feces, 5 people per day, and 4 kilograms of urine in 4 hours. So only part of a day, a solar day. Once again, we're going to have to continue altering the system moving forward for things like storage for cloudy days and making it more efficient and economical as we move forward. But right now, we know our end goal is to make a valuable product, where the nice thing is that we're not using the intrinsic value, the intrinsic energy in the feces in order to run our processing. This is all off of solar energy, and then we're able to sell basically the energy that's intrinsic in the feces as a product, as a valuable product afterwards. And to that end, you can go to the next slide. We're measuring different energy contents in the char that we're producing. We've run experiments with real human waste from 300 degrees Celsius to 750 degrees Celsius. The lower temperature is shown to be competitive in the solid fuel market, even with just it not being a traditional biochar or charcoal feedstock. You can go to the next slide. And we're also evaluating it as soil amendment and adsorbance. So we've run some experiments around these properties that are listed here that tend to be seen as important factors when you're making biochar as a soil amendment. And also we're running experiments related to odor removal, hydrogen sulfide removal, using biochar as an absorbing media, a filter media, as well as nutrient retention from a urine stream. We have some data. We don't have time for that today, though, so next slide. So overall, this is just an overview of some of the accomplishments we've had in the past year. Spending time trying to improve solar tracking accuracy with cheap analog controls, managing the heat that we're generating. Actually, one of the biggest problems we've had is generating too much energy and too much solar flux. So that's kind of a unique problem to have in terms of having too much energy in these settings. We're also working with partners to evaluate markets for the different products that we're looking at, from the household scale to the industrial solid fuel scale, as well as absorbance and soil amendments. And then we've also completed a bunch of experiments related to disinfection of urine. And I think that's the last slide. If you have any questions, we do have a Facebook page if you want to like us on Facebook. And I thank you guys for your time.
Thank you, Richard and Ryan, for that great. You coordinated perfectly. And it's very good listening to your self-sustained toilet, which harnesses energy from the sun. Question from Daniel Lee. Yeah, he wants to know the power density that you generate with these solar panels.
So it's that's kind of, I don't know, it depends on what you're talking about. So at the concentrator side, we're seeing about I guess about 2,000 kilowatts per meter square when you concentrate light down to the focal point that we have with our dish. At the other end, if we're transmitting about 500 watts through all 8 fibers and shining on the reactor, we have a 4-inch outer diameter reactor. So whatever that area would be, I don't know that in meters squared off the top of my head, but that would be the power density at the end. It'd be 500 watts divided by
Thank you, Richard.
that area of the reactor.
Questions from other participants? So, Richard, you saw Daniel says thank you for that answer. Yeah.
You're welcome.
Any further questions?
You're welcome. Thank you.
I think Louisa wanted to.
Okay. Yes, I said yes.
Yeah, Louisa,
sorry. Yes. Yes, sorry. No, sorry. Just a question. Are you planning to install it for a community or a public use or a household? Because it's quite a lot of. Is creator required or not for production for hours? I mean, compared with a small family. Anyway, who are your clients? I mean,
yeah, we haven't pinpointed where our field trials will be as of yet, and field partners, where we have a variety of people we're talking to, and in terms of the scale, we're At this point, the prototype is designed for a house, is around a household. We're trying to make the economics work from that perspective. But if a scale up would probably be able to increase the efficiency and things like that. But at this point, we're really targeting a household or shared toilet level. Of course, optimizing the technology, making it more efficient, and learning a bit more about it will inform up to waste processing capacities, but we haven't really employed that as a target as of yet.
All right, thank you very much. Yep. So if there are no further questions, then we will round up for today. It's been a very interesting discussion. Presentations were good. And we had so many participants for the first time in this series. So, Arno?
Okay, thank you. Thank you, Nelson. Yeah, I found this fascinating. We learned about the nanomembrane toilet from Cranfield, and it could be actually a big leader in terms of water conservation, the dry parts of the world that are more like spaceships, where water is worth its weight in gold. And we also learned about the fascinations around pit latrines. Most people think that pit latrines are simplistic, but they aren't. We heard about 3 fill-up rates and different kinds of biological activity. And then finally, we heard something about the use of very intensive solar power to pyrolyze feces. So all of these are fascinating in many ways, components of which will eventually lead to the reinvented toilet. And I think we're witnessing breakthroughs and changes as we speak. So I'd like to thank you all for participating today. Some of you, it's evening time. Some of you, it's the beginning of the day. We will see you again on SuSanA Forum at the down part, right down here at the bottom of the screen, and also on the Sustainable Sanitation Alliance website. The next 2 webinars coming up are the 15th of January and the 4th of February. If there's any follow-up and questions at all, and that's for those of you seeing the recording as well, please bring this up. There'll be a special spot in the SuSanA Forum for you to get your voices heard and get your answers to some of your questions. So without any